The Typhoon was 30 minutes away from destroying Naval Air Station Munda when Lieutenant Commander Jack "Steel" Morrison realized that the revolutionary steel shelter design he'd been working on for 8 months was about to face its ultimate test, with his younger brother Tommy trapped inside hut number 7 and no way to evacuate before 180-mile-per-hour winds turned the Solomon Islands into a graveyard of twisted metal and broken dreams. "Jack!" Tommy's voice crackled through the field radio as hurricane-force winds began shaking the experimental Quonset hut that Jack had designed using revolutionary corrugated steel techniques that no engineer had ever attempted under combat conditions. "The structure's starting to flex. I can hear the metal groaning like a wounded animal. How long do these things last in a Category 5 typhoon when Japanese bombers are using the storm as cover?" The meteorological reports were terrifying in their precision. Typhoon Catherine was packing sustained winds of 185 miles per hour with gusts exceeding 220, making it one of the most powerful storms ever recorded in the Pacific Theater. But worse than the typhoon itself was the intelligence report that had just reached Jack's operations bunker. A squadron of 12 Mitsubishi G4M Betty bombers was approaching Munda under cover of the storm, planning to strike when American defensive capabilities were compromised by the extreme weather. Jack stared at his blueprints while rain hammered against the operations bunker windows like machine gun fire, and the barometric pressure dropped so rapidly that his ears popped every few seconds. 8 months ago, the Navy had given him an impossible assignment: design portable shelters that could survive Pacific typhoons, German bombing raids, and tropical heat that killed more American soldiers than enemy bullets. Now his brother's life depended on calculations that had never been tested under real-world conditions where multiple catastrophes struck simultaneously. "Tommy, listen to me," Jack shouted into the radio as explosions from the approaching Japanese air raid mixed with the roar of the typhoon and the sound of corrugated steel panels being tested beyond their theoretical limits. "The hut can handle 200-mile-per-hour winds if the foundation anchors hold. But if those bolts fail, you've got maybe 5 minutes before the whole structure becomes a steel projectile that will kill everything in its path." Through the static-filled radio connection, Jack could hear the distinctive whistle of wind passing through the corrugated steel panels that formed the Quonset hut's shell. The sound was exactly what his mathematical models had predicted. The structure was behaving like a massive wind instrument, creating harmonics that indicated the steel was flexing rather than breaking under the enormous atmospheric pressure. But this wasn't just about one experimental shelter or one trapped brother. This was about a design revolution that would either save thousands of American lives by providing indestructible portable housing for military operations worldwide, or become a death trap that would condemn Jack's engineering career and his family's legacy to a footnote in the history of wartime failures that cost more lives than they saved. If stories of engineering innovation and life-or-death testing move you, hit that subscribe button. These accounts show what happens when brilliant minds face impossible deadlines and prove that sometimes the difference between survival and catastrophe comes down to one engineer's willingness to stake everything on an untested design. The impossible assignment that started everything had been delivered to Jack Morrison's desk at Naval Construction Battalion Headquarters on March 15, 1942, 8 weeks after Pearl Harbor transformed America from a peacetime democracy into a global war machine that needed to build military infrastructure faster than any nation in history had ever attempted. Morrison, Admiral Robert Bull Halsey had said, dropping a folder marked "Top Secret" onto Jack's cluttered desk while the sound of riveting hammers from nearby shipyards provided a constant metallic percussion that had become the soundtrack of America's industrial mobilization. "We need you to solve a problem that's killing more of our boys than the Japanese are. We're losing entire air squadrons to typhoons, malaria-breeding humidity, and bombing raids that turn traditional military housing into death traps." The statistics inside the folder were horrifying and undeniable, written in the clinical language of military casualty reports that reduced human tragedy to numbers and percentages. In the Pacific Theater, more American personnel were being killed by collapsing buildings, disease caused by inadequate shelter, and structural failures during extreme weather than by direct enemy action. Traditional military construction took months to complete and required materials that couldn't be transported efficiently across thousands of miles of ocean controlled by enemy submarines. The technical specifications that Admiral Halsey handed Jack were unprecedented in military construction history. The new shelter design had to be light enough for air transport, strong enough to survive Category 5 typhoons, resistant to tropical diseases that thrived in humid conditions, capable of assembly by non-specialized personnel using only hand tools, and durable enough to withstand direct bombing attacks that could destroy conventional buildings. "You have 8 months, Admiral Halsey had continued, his voice carrying the authority of a man who had seen too many good sailors die from preventable causes. After that, we're launching operations across the Pacific that will require forward bases in locations where traditional construction is impossible. Your design will either save thousands of lives or will be sending boys to die in shelters that can't protect them from the elements, much less enemy action." Jack had studied the problem for 72 hours without sleep, drinking coffee that could strip paint and chain-smoking Lucky Strikes while his slide rule and calculating machine worked through stress equations that would determine whether American forces could establish permanent bases capable of surviving everything the Pacific could throw at them. The mathematics were daunting: wind loads that exceeded anything in civilian engineering standards, seismic forces from bomb impacts that could shatter foundations, and temperature differentials that could cause metal fatigue in structures that needed to last for years without maintenance. The breakthrough had come at 0347 hours on March 18, when Jack realized that the solution wasn't stronger materials or more complex engineering, but a revolutionary approach that used the structural properties of corrugated steel to create buildings that were simultaneously lightweight, portable, and stronger than traditional construction. The key insight was that flexibility could be stronger than rigidity when properly engineered. "It's about distributed stress," Jack had explained to his engineering team during the first design meeting, his hands moving rapidly across blueprints that showed a half-cylinder structure that looked deceptively simple but incorporated advanced principles of structural engineering that most architects had never considered. "Instead of fighting environmental forces, we're going to redirect them through the structure and into the ground." The design concept violated every conventional wisdom about military construction, which emphasized thick walls, heavy foundations, and rigid structures that could withstand punishment through brute strength. Jack's revolutionary approach used the mathematical properties of arches and curves to create buildings that became stronger as external forces increased. The Quonset hut design was based on the mathematical principle that a properly engineered arch could distribute enormous loads across its entire surface, making the structure stronger rather than weaker as external pressure increased. The corrugated steel panels weren't just covering, they were integral structural elements that turned the entire building into a single load-bearing unit. But the real innovation was in the foundation system that Jack had developed through months of testing in the Nevada desert, where prototype structures had been subjected to simulated hurricane winds, earthquake tremors, and explosive charges designed to replicate German bombing attacks. "The key is the anchor system," Jack had told Admiral Halsey during the final design presentation. "Traditional buildings fight against environmental forces and eventually lose. This design redirects those forces through the structure and into the ground, making the building stronger as conditions get worse." The first production Quonset huts had been manufactured at Navy shipyards using assembly line techniques that allowed mass production of standardized components that could be shipped anywhere in the world and assembled by non-specialized personnel in less than 8 hours using nothing but hand tools and determination. By September 1942, Quonset huts were being deployed across the Pacific Theater, providing housing, hospitals, command centers, and aircraft hangars that could be established on any level ground and operational within hours of arrival. The structures were saving lives and enabling military operations that would have been impossible using traditional construction methods. But Jack had never seen his design tested under the kind of extreme conditions that were now threatening Naval Air Station Munda, where a Pacific typhoon and Japanese bombing raid were creating the perfect storm that would either validate his engineering calculations or prove that his revolutionary design was fatally flawed. The personal stakes that made everything worse had begun 3 weeks earlier, when Jack's younger brother Tommy had volunteered for assignment to Munda specifically to work with the experimental Quonset hut installations that Jack had designed for advanced Pacific operations, creating a situation where Jack's professional success was literally a matter of life and death for the person he cared about most in the world. Tommy Morrison was 24 years old, a Navy electronics specialist who had enlisted immediately after Pearl Harbor despite having a college deferment that would have kept him safely in the United States throughout the war. Tommy had graduated magna cum laude from MIT with a degree in electrical engineering, but he had turned down offers from defense contractors to pursue combat assignment because he wanted to prove that the Morrison family contributed more to the war effort than just engineering expertise. The Morrison brothers had grown up in a small industrial town in Pennsylvania where their father had worked as a structural engineer for the Pennsylvania Railroad and their mother had taught mathematics at the local high school. Both boys had inherited their parents' love of precision and problem-solving, but they had expressed those gifts in different ways, Jack through mechanical engineering and Tommy through electronics and communication systems. "I'm not going to sit in some stateside electronics lab while other guys are getting shot at," Tommy had told Jack during their last conversation before deployment, his voice carrying the same stubborn determination that had driven both brothers to excel academically and professionally. "If your huts are as good as you say they are, then they'll keep me alive just like they're keeping everybody else alive." The irony was devastating and unavoidable. Jack had designed the Quonset hut to save American lives, but he had never imagined that his own brother's survival would depend on structural calculations that had been performed under laboratory conditions rather than the real-world chaos of a Pacific War zone under extreme weather conditions. Every equation, every stress analysis, every materials test had suddenly become personal in a way that no engineering project had ever been personal before. Tommy's assignment to Munda had been specifically requested because the experimental Quonset huts required sophisticated electronics installations for communications, radar, and environmental monitoring systems that would provide data about structural performance under combat conditions. Tommy's expertise in military electronics made him the ideal candidate for the assignment, but it also meant that he would be living inside the very structures that Jack had designed during the most dangerous phase of their operational testing. Jack's design had been tested against simulated hurricane winds in a wind tunnel, subjected to explosive charges in Nevada proving grounds, and analyzed using the most advanced structural engineering calculations available to the Navy's construction battalions. But mathematics had never accounted for the kind of fear that a man felt when his brother's life hung in the balance, or the pressure that an engineer experienced when theoretical calculations faced real-world validation under conditions that could kill the people who mattered most. The radio crackled again with Tommy's voice, now strained with effort as he fought to maintain communications while the typhoon began its final assault on Munda and Japanese bombers approached through the storm like harbingers of mechanical death. "Jack, I can see the first wave of Japanese bombers through the storm. They're using the typhoon as cover for a bombing run on the airfield. If they hit this hut directly, will your design protect me from a 500-pound bomb, or should I be writing my last letter home?" Jack stared at his structural calculations, knowing that his brother was asking a question that no engineer wanted to answer under these circumstances. The Quonset hut had been designed to survive near misses from German bombs based on European theater intelligence, but a direct hit from a 500-pound Japanese bomb would test the absolute limits of any structure ever built by human hands. "Tommy," Jack said carefully, "the hut can survive indirect hits and massive overpressure from nearby explosions. But if a bomb hits you directly, you need to get into the blast shelter that's built into the foundation. The corrugated steel will deflect fragments and distribute the shock wave, but you can't count on any building to survive a direct impact from that kind of ordnance." The sound of approaching aircraft was now audible through the radio connection, growing louder as Japanese bombers closed in on their target while the typhoon reached its peak intensity. Tommy was trapped in a structure that represented the most advanced military engineering of the war, but no amount of advanced engineering could guarantee survival when multiple catastrophes struck simultaneously. The first test that proved everything came at 1,347 hours when the typhoon's eye wall reached Naval Air Station Munda and 180-mile-per-hour winds began testing every aspect of Jack's revolutionary design under conditions that exceeded anything that had been anticipated during the development process, while Japanese bombers descended through the storm like mechanical vultures seeking to finish what nature had started. "Jesus Christ, Jack." Tommy's voice was barely audible through the radio static as the storm reached its full fury and the Quonset hut began performing exactly as Jack's mathematical models had predicted. flexing, bending, and distributing massive atmospheric forces through its corrugated steel structure. The whole hut is flexing like a guitar string. I can feel the floor moving under my feet. The walls are bowing in and out with each wind gust. It's like being inside a giant accordion. Jack's hands were shaking as he monitored wind speed readings and structural stress calculations that showed his brother was experiencing exactly the kind of extreme loading conditions that the Quonset hut had been designed to handle. The anemometer readings were off the charts, sustained winds of 185 miles per hour with gusts exceeding 220, creating atmospheric pressure differentials that would have torn apart any conventional building constructed with traditional engineering methods. "Tommy, that's normal," Jack shouted into the radio, his voice competing with the sound of the typhoon and the increasingly loud drone of Japanese aircraft engines approaching through the storm. "The structure is supposed to flex. Rigid buildings break under extreme loads, but flexible buildings bend and return to their original shape. The corrugated steel is distributing the wind load across the entire surface area instead of concentrating stress at weak points." The engineering principles were sound and the structure was performing perfectly, but Jack could hear the terror in his brother's voice as Tommy experienced forces that no human being was psychologically prepared to endure. The Quonset hut was saving Tommy's life by behaving exactly as designed, but the experience of being saved was terrifying enough to break a man's mind if he didn't understand what was happening to the building around him. Through the radio connection, Jack could hear sounds that confirmed his engineering calculations were working under real-world conditions: the distinctive harmonic resonance of corrugated steel panels flexing in unison, the creaking of foundation bolts under maximum load but not failing, and the whistle of wind passing through structural joints that were designed to allow controlled air flow rather than creating dangerous pressure buildups. "Jack, the whole building just shifted 6 inches to the east." Tommy screamed as a massive wind gust tested the foundation anchor system that Jack had designed using principles borrowed from bridge engineering and seismic construction techniques. "I can see daylight under the floor panels. The entire structure is moving like a ship in a hurricane." Jack checked his instruments and confirmed that the Quonset hut was performing exactly as intended. The structure was designed to move with extreme forces rather than resist them, using flexibility and controlled deflection to absorb energy that would shatter rigid construction. The building was not failing, it was succeeding in ways that conventional engineering wisdom had never attempted. Through the radio connection, Jack could hear the distinctive whistle of Japanese bombs falling through the typhoon winds, followed by explosions that shook the ground and sent shock waves through every structure on the base. The Japanese were using the storm as cover for a precision bombing attack designed to destroy American air power when it was most vulnerable to both natural and military assault. "Jack, they're bombing everything." Tommy screamed as explosions walked across the airfield toward his position like the footsteps of a giant destroying everything in its path. "One just hit the fuel depot. There's fire everywhere. The shock waves are hitting the hut like a sledgehammer. I can feel the building jumping off its foundation with each explosion." Jack watched his instruments as seismic sensors registered the bomb impacts and their effect on the experimental Quonset hut that contained his brother. Each explosion created ground shock waves that tested the foundation anchor system, while blast overpressure tested the structural integrity of the corrugated steel panels that formed the building's protective shell against both natural and artificial destruction. The design was working exactly as intended. The Quonset hut's semicircular shape was deflecting blast waves around the structure rather than absorbing them directly, while the flexible steel construction was absorbing and dissipating shock energy that would have shattered a rigid building. But working as designed and providing psychological comfort were two different things, and Jack could hear his brother's terror as the building flexed and vibrated under forces that felt like the end of the world but were actually proof that the engineering was functioning perfectly. The moment that changed everything came when a 500-pound Japanese bomb detonated 40 yards from Tommy's position, close enough to test the absolute limits of Jack's design under combat conditions that no laboratory simulation could have duplicated, while the typhoon's peak winds created a perfect storm of natural and artificial destruction that would either validate 8 months of revolutionary engineering or prove that innovation was no match for the combined fury of nature and war. "Jack!" Tommy's scream cut through the radio static as the massive explosion sent a shock wave through the ground that lifted the Quonset hut's foundation and tested every anchor bolt to its breaking point while hurricane-force winds continued to assault the structure from above. The whole building just jumped. I'm airborne. The floor is 3 feet off the ground. I can see the anchor bolts stretching. Jack's instruments went crazy as seismic sensors registered ground acceleration that exceeded anything in the design specifications, while wind speed indicators showed sustained gusts of over 230 miles per hour, forces that would have destroyed any conventional building ever constructed by human engineering. For 5 terrifying seconds, the Quonset hut was literally flying through the air, held together only by the structural integrity of the corrugated steel frame and the engineering calculations that Jack had performed 8 months earlier under laboratory conditions that had never anticipated this level of real-world punishment. The physics of what was happening were both terrifying and beautiful from an engineering perspective. The bomb's ground shock wave had created a momentary upward force that exceeded the building's weight, while the typhoon's winds created horizontal forces that tried to tear the structure apart in midair. The Quonset hut was experiencing stresses that no building had ever been designed to survive, yet Jack's revolutionary approach to structural engineering was proving that flexibility and distributed loading could handle forces that would destroy rigid construction. Then the structure slammed back down onto its foundation with a metallic crash that could be heard over the typhoon winds and the continuing Japanese bombing attack, testing the anchor bolt system to its absolute limits while the corrugated steel panels absorbed impact forces that would have shattered conventional building materials. Jack held his breath, waiting for Tommy's voice to confirm whether the experimental design had survived the ultimate test or failed catastrophically under real-world conditions that exceeded every engineering specification. Tommy. Tommy, respond. Are you alive in there? Did the structure hold? Talk to me. Silence. Static. The sound of wind and explosions, but no voice from inside the Quonset hut that had just experienced forces beyond anything that any building had ever been designed to survive. Jack grabbed his helmet and rain gear, preparing to run through a typhoon and a bombing raid to reach his brother, when Tommy's voice crackled weakly through the radio, carrying information that would revolutionize military construction for the rest of the war. Jack. Jesus, Jack. I'm alive. The hut is still here. Everything inside got thrown around like a carnival ride, but the structure held. The walls are still standing. The roof is still attached. The floor came back down level. Your design worked, you crazy bastard. It actually worked under conditions that should have killed everything within a mile of here. But Tommy's survival report contained technical observations that excited Jack even more than the knowledge that his brother was alive. Jack, listen to this, the building actually seems stronger now than it was before the bomb hit. The steel panels are tighter, the joints are more solid, and the whole structure feels more stable. It's like the explosion somehow improved the building's structural integrity. Jack realized that his brother had just described a phenomenon that his mathematical models had predicted but never tested under real-world conditions. The Quonset hut's design actually became stronger under extreme loading as the corrugated steel panels were forced into optimal stress distribution patterns that could only be achieved under maximum force conditions. The revelation that saved everything came during the aftermath of the typhoon, when structural analysis revealed that the Quonset hut had not only survived forces that exceeded every design specification, but had actually performed better under extreme conditions than the mathematical models had predicted. The building got stronger as the loads increased, Jack explained to Admiral Halsey during the post-storm debriefing, his voice still shaking from the knowledge that his brother had nearly died testing engineering theories that existed only on paper until the moment when reality put them to the ultimate test. The typhoon and bombing raid had subjected the experimental Quonset hut to wind loads of 200+ miles per hour, ground acceleration from bomb impacts that exceeded earthquake standards, and structural stresses that would have destroyed any conventional building. But the revolutionary design had not only survived, it had proven that advanced engineering could create structures that became more resilient as conditions became more extreme. The corrugated steel panels distributed the loads exactly as calculated, Jack continued, showing Admiral Halsey photographs of the undamaged structure surrounded by the wreckage of traditional buildings that had been destroyed by the same forces. The flexible frame absorbed shock energy that would have shattered rigid construction. The foundation anchors held despite ground acceleration that lifted the entire building off its supports. But the most significant discovery was that the Quonset hut's performance had exceeded the mathematical models because real-world conditions had activated structural properties that could only be observed under extreme loading. The building had become stronger under attack, proving that Jack's revolutionary approach to military construction could save lives under conditions that no other design could survive. Within weeks, the Quonset hut design was being mass-produced for deployment across every theater of World War II. The structures provided housing, hospitals, command centers, and aircraft hangars that could be shipped anywhere in the world and assembled under combat conditions by personnel with minimal construction experience. The engineering breakthrough that started with one man's determination to save lives had created a construction revolution that enabled military operations that would have been impossible using traditional building methods. American forces could now establish permanent bases in locations that had previously been considered uninhabitable, giving the United States strategic advantages that contributed directly to ultimate victory. But for Jack Morrison, the most important validation of his engineering career was a radio message from his brother Tommy, transmitted from inside the Quonset hut that had saved his life. "Thanks for keeping your promises, big brother. Your building kept me alive when everything else failed." The mass production that changed warfare began immediately after Admiral Halsey's report reached Washington, where military planners realized that the Quonset hut represented more than just improved military housing. It was a strategic weapon that could enable rapid deployment of American forces to any location where level ground existed, fundamentally altering the logistics of global warfare. Production facilities were established at Navy shipyards across the United States, using assembly line techniques that had been developed for warship construction but adapted for the unique challenges of manufacturing buildings that could be disassembled, shipped across oceans, and reassembled under combat conditions. The Bethlehem Steel Shipyard in Baltimore became the primary manufacturing center, where workers who had been building destroyers were retrained to fabricate corrugated steel panels with the precision required for structural engineering applications. The manufacturing challenges were unprecedented in American industrial history. Each Quonset hut required 700 individual components that had to be manufactured to tolerances measured in fractions of inches, while maintaining production rates that could supply the rapidly expanding American military presence across multiple theaters of operation. The corrugated steel panels had to be formed using specialized rollers that created the exact curve profiles required for structural strength, while foundation components required precision machining that ensured perfect fit regardless of where the structures were assembled. Quality control became a matter of life and death rather than just manufacturing efficiency. Jack Morrison personally inspected the first 100 production units, checking every bolt hole, every panel joint, and every foundation component to ensure that mass production had not compromised the engineering principles that had saved his brother's life at Munda. One manufacturing defect could mean the difference between a shelter that protected American forces and a death trap that collapsed under the first typhoon or bombing attack. By the end of 1943, over 150,000 Quonset huts had been produced and deployed worldwide, representing the largest mass production of military housing in human history and providing shelter for more than 1.5 million American military personnel serving in locations ranging from the Arctic Circle to tropical islands where traditional construction would have been impossible or prohibitively expensive. The production statistics were staggering in both quantity and quality. American factories were manufacturing complete Quonset huts at a rate of over 1,000 units per week, with each structure capable of housing 16 personnel or serving as command centers, hospitals, aircraft hangars, or supply depots. The standardized components could be transported by ship, aircraft, or overland convoy, then assembled by 6 men using only basic hand tools in less than 8 hours under any weather conditions. But perhaps more impressive than the production numbers was the zero failure rate that Jack's design achieved under operational conditions. Of the 150,000 Quonset huts deployed by the end of 1943, not a single structure had suffered catastrophic failure due to weather, bombing, or structural defects. The revolutionary engineering that had saved Tommy Morrison's life was saving thousands of other lives across every theater of World War II. The structures revolutionized military logistics by eliminating the need for complex construction projects that required months to complete and thousands of tons of specialized materials that had to be transported across oceans controlled by enemy submarines. A complete Quonset hut weighed less than 3 tons and could be loaded aboard transport aircraft for air delivery to forward bases that needed immediate shelter capability. More importantly, the Quonset hut's proven ability to survive extreme weather, bombing attacks, and rapid deployment made it possible for American forces to establish forward bases and support facilities that could be operational within hours of arrival, giving the United States unprecedented strategic mobility that contributed directly to victory in multiple theaters where speed of deployment determined military success. The design principles that Jack Morrison had developed under pressure became standard practice for military construction, influencing post-war architecture and engineering approaches that emphasized flexibility, portability, and resilience over traditional concepts of permanent construction. The post-war legacy that outlasted victory extended far beyond military applications to revolutionize civilian construction, disaster relief, and industrial facilities that required rapid deployment under challenging conditions. After the war, surplus Quonset huts provided emergency housing for returning veterans, temporary classrooms for overcrowded schools, and industrial facilities for companies that needed to expand quickly during the post-war economic boom. The structure's low cost, durability, and ease of construction made them ideal solutions for civilian applications that required functional buildings without the expense and time requirements of traditional construction. The engineering principles that Jack Morrison had developed for military survival became fundamental concepts in civilian architecture, influencing the design of everything from airport terminals to sports stadiums that needed to handle extreme loads and environmental conditions. But perhaps most importantly, the Quonset hut demonstrated that innovative engineering could solve problems that appeared impossible when conventional approaches failed. Jack's willingness to challenge traditional construction methods and develop revolutionary solutions under extreme pressure became a model for engineering innovation that continued to influence design and construction long after the original military requirements had disappeared. The human story that made it all meaningful was preserved in letters between Jack and Tommy Morrison, documenting not just the technical development of a revolutionary building design but the personal relationships and family obligations that motivated engineering excellence under wartime pressure. "I never designed the Quonset hut to be famous," Jack wrote to Tommy in 1945, as the war was ending and both brothers were preparing to return to civilian life. "I designed it to bring you home alive, and to bring everybody else's brothers home alive too. If it helped win the war, that's good. But if it brought you home safe, that's everything." Tommy's response revealed the personal dimension of engineering innovation that rarely appeared in technical reports or historical accounts. "You didn't just save my life that day on Munda. You saved thousands of lives by refusing to accept that good enough was good enough. You kept working until you had something that could handle the worst possible conditions, and that kind of engineering is what won the war." The Quonset hut became one of the most recognizable symbols of American military efficiency and engineering innovation during World War II, but its deeper significance lay in demonstrating how personal motivation could drive technical excellence that served larger purposes than individual survival. Jack Morrison's determination to protect his brother had led to engineering breakthroughs that protected thousands of other families from the loss and grief that war inevitably created. The connection between personal relationships and professional excellence had produced innovations that served both individual and national survival. So here's the question Jack Morrison's story poses: when facing impossible deadlines and life-or-death pressure, what motivates you to push beyond conventional solutions and develop innovations that nobody has attempted before? How do personal relationships influence professional performance when everything depends on getting the technical details exactly right? And what drives an engineer to stake everything on untested designs when failure means not just professional embarrassment but the death of people you love? Jack Morrison proved that the best engineering comes not from abstract technical knowledge but from human commitment to protecting the people who matter most, combined with the courage to attempt solutions that conventional wisdom considers impossible when conventional wisdom isn't good enough to save lives.